Okay, so we're going to briefly take an overview of the practical here in this portion, but please see the demonstration video where we go through the technical steps for this practical. So this is just background information. So firstly, like the other practicals, ideally you'll have some data you want to examine, and you can use, if you did the course G01 in QC or the one on G02 assembly, you should have QC SARS-CoV-2 data you can use if you want to. So be able to use short read data and long read data. That's our key goal here. So what we're going to do is we're going to map reads with minimap2. We're also going to map reads with BWA mem2. Arguably, minimap2 works better for long reads. BWA mem works better for short reads, but that's quite a contested point. And then we'll process the data with samples and look at how we can extract quality metrics from that. And then in the same way, we'll visualize the quality of our read mapping with QualiMap as well. So key things are that at least one read mapping tool are definitely essential. SAM2 again is essential for sample to bound processing, and QualiMap is optional, but it's a nice visualization tool. So if you feel an important read library, it will be important to examine it in detail. If you're trying to find libraries, you can find ones at this location that should be accessible to you. If they're not, just give me a shout and I'll make sure that they are. What we're going to do in practical, if you're not sure that you have libraries you want to examine, is we're going to look at the SARS-CoV-2 example, look at that genome structure of your samples compared to other samples. And you might find that there's certain regions that have low complexity within there. So what we're going to do is take those reads and map them with minimap2, which is this name on the computer, and BWA mem2, which is that name on the computer. It has a mem function that will call as well and use that too. So goal in this practical is to index our reference sequence. We're going to map our single end reads, but that's what we do with the SARS-CoV-2 data, from a single FASTQ file to the reference. If we're dealing with parent end reads, it's pretty much the same thing. And we'll also look at how we can tweak it for longer reads as well. So there's certain parameters for longer reads with nanopore, PacBy, or whatever you have. We're going to look at minimap2, but also BWA mem. So BWA is the older program that has been improved since, but BWA mem, and then also BWA mem2. So we're using the newest version that should work more effectively. And this is useful if we're mapping our short reads to a closely related reference. And they can also map longer reads too. So BWA mem2 and minimap2 are quite flexible. So with BWA, we will do this pretty much the same steps. Index our reference, map single end reads, and then also map paired end reads. We'll do all those steps, and you can choose whichever one of these maybe it works best for you. We'll use this toolkit, known as SAM tools, which contains a bundle of functions like view and sort to do different things to our read libraries. And this is essential to convert our SAM file into a BAM file, to sort that, to remove duplicates, and to view those reads properly. So we'll look at how we can have particular commands with this format where we have some reference genome, some location we want to look at, and then we can look at the basis where here we have the commas showing our verse read with no difference to the reference, and the full stop, which are not shown here, again with no difference to the reference, whereas here we can see that there's probably a TG snip here based on the consensus. But we also see that there are random kind of errors at certain places in reads, and that can and then that's always going to occur. So we can actually view this with SAM tools. We'll also look at how we can extract summary stats using this flag stack command with SAM tools, and that will give us information to maybe make a table like this, where this is our one sample mapped with minimap2 and BWA mem2, and the same for the other sample. I'm just using their accession number IDs, minimap2 and BWA mem2. We have the total number of reads, so you can see that they're different, and importantly, you see minimap2 and BWA map equivalent amounts, but not the exact same. The number of map reads, again, it differs. That's slightly lower for minimap2. You can see there, and you can see that there's very few that contain paired end information in this example. It's single end reads. You can also read more about PolyMap2 at its website there, but basically it visualizes the key information for our libraries, out of which is covered already. But for nanopore data, it will tell us like the mean coverage, the standard deviation, mean mapping quality, the error rate for insertions and deletions, the numbers that are found, which are quite high here, as you can see, across, if you look at every read that's present. We have about 16,000 reads, mapping to our SARS-CoV-2 reference of 29.9 kb. It is no unmapped reads, which is good. Duplicate reads, you always expect that there'll be a high duplication rate. And what we can see when we visualize that further and look at the coverage across the genome, so the coverage, the genome is listed here on the x-axis, and this is the fold coverage. You can see that there's definitely apical sequencing here because we see a spike in between each of the middle regions. I see some regions that have much lower coverage. So there's probably enough there to assemble this well, but you might find there's certain gaps in our assembly too at certain regions that just have low coverage. We also know that if we try to de novo assemble this alone and there's insufficient reads at each of these boundaries, like here and here, that may not assemble altogether as a single contig. We can also look at things like the Hubble polymer rates and other error rates and kind of explore if there are artifacts that might affect, say, our capacity to identify indels. So that's the end of this video on the practical overview. So please look at the demonstration videos or look at the hands-on approach of how we want to map reads to reference genomes, look at their read qualities, how we can achieve these goals of trying to map short and long reads to reference genomes and use read mapping to inform our genomic results. So please look at those demonstration videos further.